Okay, welcome to our first video on our impulse and momentum unit. This represents a shift into obviously a new unit, a new topic, a new chapter, if you will, but it also represents a shift into a slightly different branch of mechanics. So far, what we've been focusing on is kinematics and forces for the most part, and that's one good way to measure and determine what's going on around you and to predict what's going to happen in the natural world. What we're going to do over the next month and a half to 2 months or so is we're going to look at another way to look at to make measurements and make predictions about the world. So far we've really talked a lot about kinematics and forces. The next 2 months are going to be dedicated to impulse, momentum, and energy. So let's start off. Impulse. Just a real quick question. It's actually, we're going to link this, and we're not doing something totally different. What we're going to do, though, is start by kind of linking how you might get this out of kinematics and forces. So, example question, which of the following applied forces would cause a 2 kilogram object to have a higher final speed at the end of the allotted time period if the object starts from rest? A 1 Newton force that acts for 5 seconds or a 0.6 Newton force that acts for 10 seconds? So notice that in both cases you are given the net force and the time, and we want to know the final speed, and we're told that the object starts from rest, so that's VI is 0 meters per second, and we're given the mass. So we're given a whole bunch of things here. We're given net force, mass, the final speed, the initial speed, and the time. And we're going to see which of these objects will have a higher final speed. Now, you might be looking at that speed and saying, okay, well, we have the initial speed and the time, so why don't we use the Fiat equation? And that's a good idea, but we don't know the acceleration. So that's a bit of a problem there. But that's not a big deal, because we're told the mass of the object and we have the net force that is acting on the object. So if we can use Newton's second law to find the acceleration, we can then use the Fiat equation to find the final speed. That's going to look something like this. So here's for the first bullet point. Okay, F net equals ma. The net force is 1 Newton. The mass is 2 kilograms. So the acceleration is 0.5 meters per second squared. And we use that acceleration in the Fiat equation. VI is 0, VF is what we're looking for, 0.5 meters per second squared times 5 seconds. Final velocity is 2.5 meters per second. Now what I really should have had you done at the outset is think about this without actually doing the calculations. What do you think is going to be which one of these do you think is going to have the final speed? Is it the example where there's a bigger force but for a shorter period of time, or is it the example where there's a smaller force but for a longer period of time? Okay, those are your two things that you kind of have to weigh. Everything else is the same. Let's do the second bullet point now. The net force this time is 0.6 newtons. The mass is still 2 kilograms. So the acceleration is 0.3 meters per second squared. And therefore we have 0.3 meters per second squared multiplied by 10 seconds. Final velocity is 3 meters per second. So it turns out that this one is the winner. The smaller net force for a longer period of time. In this case, like we just said, the smaller force eventually causes a higher final speed to be reached because that smaller force acted on the object for a long enough time. So it's not necessarily just how big the force is. It's also how much time that force acts for that can determine the final velocity. So I think this is probably pretty obvious. If we were to kind of make a generalization here, if you want something to really have a high final velocity, or maybe let's put it this way, if you want something to really change its speed a lot, you want a big force that acts for a long period of time. that will cause big changes in an object's motion. It will cause it to speed up or slow down the most. Now, it turns out that the product, meaning when we multiply them together, the product of the average net force on an object and the time that the force acts on the object is known as the impulse on the object. Okay? So we're getting a new equation right now and a new variable to deal with. Impulse, if you look on your reference tables, is actually symbolized by J. It's not symbolized by I. And if you remind me in class, I'll tell you the story of why it's symbolized by J and not I. It's a good one. So in general, if you're looking for, okay, so you're saying, okay, the product of the net force and the time, great, it's the impulse. What does that really mean? Ultimately, what the impulse does is it shows you how much an object's, and I'm going to put this in quotes, its motion has changed. It's a very general statement. And we'll talk a little bit more about what impulse means as we go on through this unit. This is a fairly short unit. We'll be done with this in about 3.5 weeks. In any case, the equation that we just discussed, impulse, is the product of the net force multiplied by the time. That is given by this equation right here. We're going to go all the way down here, so we've got some of our forces equations here. And you see this J equals F net times T. Ignore this for a second. J equals F net times T. That's what we're looking for here. So we have J equals F net, the net force, multiplied by the time. The impulse is equal to the average net force on an object multiplied by how much time that average net force acts for. It is noted that since F net is a vector and time is not times a scalar, that means that J, the impulse, is going to be a vector quantity. The units, as you can see from this, the units of net force are newtons, the units of time are seconds. The units are Newton seconds, newtons times seconds. But we could also write those slightly differently. Remember that a newton is really a kilogram times a meter per second squared. That's the definition of a newton. And if we multiply that by seconds, this S and this S squared, well, one set of those is going to cancel out. We're left with kilogram times meter per second. Okay, so you can use either one of these for the units, Newton seconds or kilograms times meters per second. Okay, not kilograms times meters per second squared, though. Those are the units of force in newtons. So let's do some practice. What impulse is given to an object that is acted on by a force of 43 newtons west for 2.7 seconds? Let's write our equation. J equals F net times time. Let's see, the force is 43 newtons. The time is 2.7 seconds. So J equals 116.1. I'm going to go with Newton seconds. And it is important that since we were told the direction of the force, the impulse is always in the same direction as the net force. So if the net force was to the west, the impulse is to the west. So the full answer is the impulse is 116.1 Newton seconds to the west. Second example, if an impulse of 12 Newton seconds south is caused by a force that acted on an object for 0.15 seconds, what was the average force on the object? So this time we're given the impulse, we're looking to find the force. So let's see here, we have 12 Newton seconds equals F net times, let's see, 0.15 seconds. How do we solve for F net? We divide the 0.15 over to the other side. So it's 12 divided by 0.15 net F net, the net force on the object due to this impulse and how much time it acted for, is 80 newtons. And since the impulse was to the south, that means the net force must also have been to the south. Okay, so there's two quick, easy examples. A force of magnitude 500 newtons causes an impulse of magnitude 2850 newton seconds on an object. How long did the force on the object last? Once again, we are being asked to solve for the time here. How long did the force last? J is 2,850 newton seconds. The force is 500 newtons. We're not told anything about the direction here, so we're just looking for, and I guess we don't need a direction if we're just solving for time, but it is important to note that usually both impulse and net force have a direction. But in this case, we just know that they're in the same direction. They're always going to be in the same direction. But time is a scalar, so we don't have to say like 5 seconds east. That doesn't even make any sense. So we're solving for the time. We divide 2,850 by 500, and we get 5.7 seconds. In other words, if that force acted and produced this much of an impulse, it must have acted for 5.7 seconds, the time that the net force acted for. Now, that's very all well and good. That's great, okay, that we can measure the impulse if we know the net force and we know the time. Let's talk about some realistic, I got some things that are going to restrict how useful this is. Now, measuring time is easy, that's fine. Measuring the net force, we've done a bunch of very, fairly basic examples up to this point in trying to figure out the net force on an object. In the real world, it's a little bit more difficult to find the net force on an object, because a lot of objects we can't just symbolize as dots or points. Everything in this class we're going to be able to, but in reality, it's a little harder, okay, especially if you have like a very complex object. What if you have an object with multiple like moving parts, and those different moving parts all have different accelerations, or there's an object that's putting a force on that other object, and it's putting different amounts of force in different parts of it. So imagine, for example, the way I usually show this in class is I have a great video of an NFL lineman hitting and throwing this little nerdy sports science guy, and I'll show you the video in class if you remind me. That example is so complex because what you would really need is you would need a whole bunch of force sensors all over the guy who's getting hit. And they are all measuring either force or the acceleration, the interaction between the two objects. They would all need to be like, I don't know, Bluetooth, I guess, and hooked up to a computer and sending them like force over time data. And then we could use a computer to kind of integrate all that together and get an impulse. That's really complicated, okay? There's actually an easier way to measure impulse. There's another equation for measuring impulse. It has to do with Newton's second law. Okay, it has to do with Newton's second law. As you remember, Newton's second law is this: F net equals ma. Okay, the very basic Newton's second law, F net equals ma. Well, let's remember this. You remember what the definition of acceleration is? We said there was an equation that kind of tells us the acceleration on an object. It turns out that the acceleration, if you remember, right on the reference table, is equal to delta v over t. So let's take this and plug it in over here, and let's rewrite this equation. We could rewrite this as F net equals mass times delta V over T, or, as I like to write, M delta V over T. Okay, F net equals M delta V over T. All we did was we took this part, and that's what we replaced acceleration with, delta V over T. What would happen if we rearrange this mathematically? What if I don't like fractions. Let's get rid of that T. Let's multiply both sides by T. We would end up with this: F net times T equals M delta V. Wait a second, we just saw this. F net times T is equal to J, the impulse. So it stands to reason that the impulse is not only equal to the net force multiplied by the time, but it's also equal to the mass multiplied by the change in velocity. It's so much easier to measure an object's change in velocity as opposed to, let's say, like the acceleration or the force on it. Okay, it's much, much easier. So all of these things are equal to each other. These two quantities right here are both can be used to measure the impulse. So what this is really showing us is that the impulse is related to the change in velocity of an object. And if we know this change in velocity and we know the mass, we can determine the impulse. Remember that this delta here, this is important. Delta always tells us the following. It tells us final minus initial. So if you have delta V, it's V final minus V initial. Final velocity minus initial velocity. If you had, let's say, delta, I don't know, if you had delta, I'm trying to think of another place where we use delta. If you had delta M, it would mean the final mass minus the initial mass. That's never going to happen in this class, but that's what it would mean. Delta, and then whatever's after it, always means change in that thing. Final minus initial. Always in that order, too. Let's do a little bit more practice here. A 6 kilogram object with an initial velocity of 3 meters per second east is accelerated to a final velocity of 5.4 meters per second east. What was the impulse that acted on the object? We were looking for J. We have the mass. we have the initial velocity, and we have the final velocity. So we don't know the net force or the time, but we do know the mass, and we know the change in velocity because we know final and initial. So here's what I would write. I would do J equals m delta V, except I'm going to expand that to m VF minus VI. Okay, and you should do that. You should expand that like that. You shouldn't just in your head say, okay, 5.4 minus 3 is 2.4. Like, we know that, but you need to show your work. You need to show exactly what they're giving you and plug those numbers in. So we're going to do J equals 6 kilograms times 5.4 meters per second minus 3 meters per second. So J, let's see, let's do the parentheses first. 5.4 minus 3, that's 2.4 times 6. J is 14.4. And let's look at those units. Kilograms times meters per second, just like we said. Kilograms times meters per second. And let's see here. We made the assumption at the very beginning of this problem, that's something I need to talk about. With these problems, because it's a vector, you have to specify direction. We had a car that was initially moving east, and it remained moving east the entire time. So when we plugged these in, 5.4 and 3, we said that they were positive. I know there's a minus sign in front of the 3, but that's because of the equation. We said they were positive. We implied that east was the positive direction. Since we get a positive answer at the end, that implies that the impulse must have been to the east. Makes sense? So we need a direction on these. A baseball with a mass of 0.1 kilograms is thrown by a pitcher with a velocity of 40 meters per second due south. Okay, so that's the initial velocity, and it says south. It's hit by a batter, so once the ball is off the bat, it has a velocity of 30 meters per second due north. Ooh, okay. That's the final velocity. We want the impulse. So the equation is going to be the same, but notice that we have vectors in opposite directions. That means right now, at the outset, we need to pick one as positive and one as negative. Because I know how this is going to work out, I'm going to say, let's assume that north is positive. So I have J equals m delta V. I don't even need to write the F net times T. I'm just going to pick the two parts of the equation that are useful to me, which is m VF minus VI. Looking for the impulse. So I know that the mass is 0.1 kilograms. V final, let's see here, V final is 30 meters per second, and that's north, so I'm going to keep that as positive. The initial velocity was to the south, so I need to put a minus sign in front of that. But notice there's a minus sign in the equation, and then I have to put another minus sign. Otherwise, I would really be implying that this is positive. But look what happens. 30 minus a negative 40 is the same as 30 plus 40. The impulse, therefore, must be 30 plus 40 is 70 times 0.1 is 7. And it's positive, so it's 7 kilograms times meters per second north, since it's positive. The impulse is 7 kilograms times meters per second to the north. Now, what if we had said south was positive? So let's just kind of imagine what this would look like. If we had said south was positive, then the initial velocity would have needed to have been negative, and I would have minus the positive 40. Negative 30 minus 40, negative 30 minus 40 is negative 70, multiplied by 0.1, that's negative 7 kilograms times meters per second. You're saying, wait a sec, that's different. Think about what we said was positive. If we said that south was positive, then a negative answer must mean north and negative, or a negative answer must mean north. We get the exact same thing. Okay? The negative or positive sign simply tells you direction. That's the only meaning of a negative or positive. It just tells you direction for vectors. A couple more examples. This is going back to that other one. If the ball was only in contact with the bat for 0.005 seconds, what was the average force exerted on the baseball? Well, we already know the impulse now. Let's go back to saying that north is positive. And we're looking for the net force, and we have the time. So 7 kilograms times meters per second equals, let's see, the net force times 0.005 seconds. We're going to divide that over to the other side. The average net force exerted on the baseball when this person hit it was 1,400 newtons. Pretty strong force. How much force is required to completely stop a 1,600 kilogram car that is initially moving at a rate of 15 meters per second in a time of 2 seconds? We're trying to stop a car. That means that the final velocity must be 0. It's stopped. The mass of the car is 1,600 kilograms. It's initially moving at 15 meters per second. That's VI, and here's the time. Notice that right here, and we're looking for the net force. Notice that here it doesn't ask us anything about impulse, and that's fine because we have this. F net times T equals M delta V. We had it right up here, it's just a rearrangement. This is basically Newton's second law, just a little bit expanded and rearranged. So we're going to use that. F net times T equals M delta V. And I'm going to expand that out. F net times T equals M times VF minus VI. We're solving for the net force. We have a time of 2 seconds. We have a mass of 1,600 kilograms. And we have a final velocity of 0 meters per second. Please put units there. And an initial velocity of 15 meters per second. Some people might want to put 15 minus 0. Think about what the final and initial velocities are. It's stopping. That means the final velocity has to be 0. The initial velocity is 15. So we're getting a negative change in velocity. That makes sense. It's coming to a stop. So the net force in this case, okay, let's do 1,600. 0 minus 15 is negative 15 times, negative 15 times 1,600 divided by 2. We get negative 12,000 newtons. Okay, what does the negative mean here? Well, we weren't given a north, south, east, west, but what it really means is opposite direction of VI. Since it was in the opposite direction of VI, since this object was slowing down, the force must have been in the opposite direction of the initial velocity. And this is important because it shows us that in any interaction that brings an object to a stop, the magnitude of the impulse will be, am I getting ahead of myself? Yes, I am getting very slightly ahead of myself. You know what? Let's save this. Let's save this for the next video, and we're going to kind of mix a couple of videos together here, because I don't think I quite have time to do the entire example. So I'm going to stop here, and we'll pick up with the next video, which will be on a topic called momentum. All right, bye.